Thanks. So thanks so much for the invitation to come here. So this will be joint work with Ling Fu and also Struve Saka, who's a student at Berkeley. Okay. So I feel a bit silly about having a slide defining TASEP because I think by this point of the workshop, if you don't know what TASEP is, I don't know what you've been doing. But okay, but maybe I'll sort of say one sort of description that will be useful to say because we'll be sort of looking at a perturbed model of TASEP. So we can think of it as for each edge that will have a rate 1 Poisson clock, and so when the clock rings, if there's a particle on the left and a space on the right, then it moves, and you keep going along like this. Okay. And the quantity that I'll be interested in is the time for the nth particle to move past the origin. And also, as has been said numerous times already, this is directly connected to last passage percolation, where you have an IID field of exponential random variables. And the time for the nth particle to cross the origin is equal in distribution for the last passage time from 1,1 to nn, where you take the maximum over all oriented paths of the sum of the field along the path. And the interpretation of the field and the coupling between the two is that Xij corresponds to the time for the ith particle to make its jth jump when you're starting with step initial conditions. Okay. And okay, so I'm really repeating things that have been said many times before, but there's a law of large numbers. You can think of, that it converges to 4. We know the fluctuations are n to the 1/3 and Tracy-Riddham distribution. Maybe that's been mentioned less often is that if you look at the optimal path and its sort of spatial fluctuations from the diagonal, the transversal fluctuations, this is known to be of order n to the 2/3, which is sort of why you get the sort of n to the 2/3 spatial scale. Okay, so that's all I'm going to say about TASEP. Now I want to perturb it and sort of study what happens when we introduce a small local defect. So we imagine that, so we have these rate 1 Poisson clocks on each of the edges, and I'll take the edge at the origin and say rather than particles jumping across that at rate 1, they'll jump at rate 1 minus epsilon. So it's a bit slower than usual. And all the other edges behave just as normal. So how does this affect the sort of large-scale behavior of the system? Okay, so that's the description in terms of TASEP. In terms of last passage percolation, well, the bond at the origin corresponds to the ith jump of the ith particle, and so rather than having being rate 1, that will be now rate 1 minus epsilon. So all in last passage percolation, it just corresponds to changing the distribution along the diagonal so that they're now rate 1 minus epsilon exponential random variables. And we want to see how this changes things. So we're now, there's a natural way of, there's multiple natural ways of coupling the two processes. But the one I want to say is that we can this slow bond process where we have bigger values on the diagonal, I'll call that the reinforced model, where we reinforced the diagonal, made them bigger. And we can make them bigger in a nice sort of way because you can write a rate 1 minus epsilon exponential random variable as a rate 1 exponential plus an independent random variable, which is like a Bernoulli times an exponential. So we could go from the original model to the slow bond one by adding IID random variables with this distribution along the diagonal. so that in particular gives you a coupling between the two models, and in such a way that what you've added to the new model is independent of the unreinforced one. So I'll talk about the original last passage percolation as being the unreinforced model and the slow bond one as the reinforced model. Okay. So we can write T and epsilon as the passage time in this reinforced model, where we've made the diagonal bigger, and this has a superadditivity property. So T and epsilon over n is going to converge to some constant almost surely. And obviously it's at least as big as 4 because we've just increased the values. And so we'll write this as kappa of 1 minus epsilon. And we want to, I want to understand this function. And so another meaning of this is 1 over kappa would be the long-term rate at which particles are going across the origin, and also the long-term rate at which they're going past any particular site, because that has to be the same everywhere. Okay, so so it's greater than or equal to 4. If it's equal to 4, then it would mean that sort of the long-term current of particles is not changed. Whereas if it were greater than 4, then that would sort of imply some sort of macroscopic slowdown of the TASEP process. Okay, so that's sort of the phenomena that we want to understand. I should say, so the model was introduced in the early 90s by Jankowski and Leibowitz, and it was analyzed by them and other groups, and they came to different conclusions. So using sort of some mean field heuristics and expansions, Jankowski and Leibowitz predicted that the critical value of epsilon, so this is like the smallest perturbation such that you have you change the current, so that such that kappa is strictly bigger than 4, is 0, meaning that for any perturbation, it should create a slowdown. On the other hand, another group of physicists, Ha, Timonen, and Denij, a bit later, doing sort of various numerical simulations, came to the conclusion that the critical value should be 0.2, around 0.2. And so these are some simulations of theirs that I stole from their paper. Here, R is just 1 minus epsilon, and delta is some sort of transform of kappa. And so such that if delta equals 0 means kappa equals 4, and that's what happens whenever, sort of what you see whenever R is bigger than 1. So R bigger than 1 would mean that you have a faster bond there, and in that case you don't expect any change in the macroscopic behavior of the system. And so certainly for R bigger than 1, it looks like you get 0 here. And for R sort of, say, less than 0.7, it looks like delta is strictly bigger than 0, which suggests you have a slowdown. But then, I don't know, it's not easy for me to look at this and say whether or not at around, say, 0.8 or 0.9, it's 0 or not. So the next thing they did was to make the assumption that if you're a bit below the critical value, that the effect of the perturbation will scale like some power law. So then if you make that assumption, then you can do sort of a log-log plot and see for what critical value gives you a sort of something that looks linear. And 0.8 was the sort of closest to linear, so that I think that's sort of essentially where the prediction comes from. If you look at values closer to 1, so say 0.9, which is the rightmost curve, it looks a bit concave, and that would correspond to having a faster than power law affect, smaller than power law affected the perturbation. Okay. There's also various rigorous work, so some upper bounds by Jankowski, Janowski, and Leibowitz, some bounds by Seppäläinen. Perhaps the most closely related work was by Bike and Rains, who looked at sort of the same problem, but in the Poissonian version. So you have a box and you have some point process, Poisson point process, except that in their version, they took the Poisson point process to be symmetric with respect to the diagonal, and then added in an extra point process along the diagonal with, so these are rate 1, and these extra ones along the diagonal are rate lambda, and you can ask the same question. So the Poissonian last passage percolation is you're looking for oriented paths that collect the most number of points, and you ask, when does this reinforcing on the diagonal sort of change the law of large number rate? And this was a model in which they could do exact computations and showed that the critical value was 1. So you needed to add a rate 1 Poisson process along the diagonal, and in particular, not 0. Okay. Unlike this model, the one we're talking about with TASEP with the slow bond is not one that seems to be amenable to exact calculations. Okay. But that would give you the wrong guess for the TASEP one, and actually with Riddhi and Vladis, we showed that Janowski and Leibowitz's conjecture was the correct one, that the critical value is 0. So for any perturbation, if you look at the law of large numbers rate, it's always bigger than 4. Okay, and I should say, once you reinforce the diagonal, the nature of the fluctuations changes. So rather than being n to the 1/3 and Tracy-Widom, they're n to the 1/2 and Gaussian. And if you look at the transversal fluctuations, rather than being n to the 2/3, you really get a pinning of the optimal path, and the typical fluctuations are just order 1. So the optimal path really closely follows the diagonal, and the maximum deviation is like logarithmic in n. Okay. So this is not the main thing I'm going to talk about, but I want to say a few words about the proof before I go forward and tell you about what happens when epsilon is positive but really small. So okay, so the proof, so the first thing you can say is that, well, T and epsilon is superadditive. So if you want to show that the law of large numbers rate is sort of bigger than 4, it's enough for some n to show that this is strictly bigger than 4n. And okay, so why is that a useful point to make? Well, the mean of, in the unreinforced case, the mean of Tn is 4n minus sort of a constant, or actually 4n plus a constant times the mean of the Tracy-Widom distribution, which is a negative number, times n to the 1/3. So you get so it's like 4n minus a constant times n to the 1/3. So we don't really need to show a linear improvement by doing this reinforcement, which you might think you need to do to prove the sort of change in the law of large numbers. We only need to show that adding this epsilon reinforcement on the diagonal increases things by a constant times n to the 1/3. Okay, so why should you expect to have that sort of improvement? 12. Okay. So let's look at the optimal path. The typical fluctuation in the unreinforced model, the typical fluctuations are n to the 2/3. So how much time do you expect it to spend on the diagonal? Well, it's sort of length n, and if it's away about n to the 2/3, then you'd expect that sort of at each point it's got probability about 1 over n to the 2/3 of being on the diagonal. So overall, you'd expect the expected amount of time to be there should be like n to the 1/3. And then along these points on the diagonal, you get a sort of, the reinforcement will give you a sort of value with a mean that's that's about epsilon, so you get an improvement overall of about epsilon n to the 1/3. And we needed a big constant times n to the 1/3, so that's not enough. But it's of the right order of the sort of improvement that we're looking for. So, but this was just saying, let's take the same path in each. It might be that taking a different path after doing the reinforcement gets you something better. So we could look for situations where there's sort of an almost optimal path that has sort of an excursion away from the optimal one, such that the cost of the two, the difference of the cost is very small. Something like delta n to the 1/3. And you can show that these sort of alternative paths will happen with probability, probability proportional to delta. So in particular with a constant probability that doesn't depend on n. And now if delta is much smaller than epsilon, and this alternative path spends a reasonable amount of time close to the diagonal, then you can get another improvement of order epsilon n to the 1/3. So we found sort of two ways to get improvements of order epsilon n to the 1/3. One is just by taking the original path and doing nothing. So this is sort of perturbation. This is like not perturbing it at all. And alternatively, taking sort of like a linear-sized perturbation here. Okay. And the trick is to look at perturbations of the original path on all different scales in between. So if this was the original optimal path, there'll be some excursions away from the diagonal that are of linear length, but some that are of length square root n or some intermediate polynomials. And you can look for sort of alternative paths in each of these excursions. And roughly speaking, what you can show is that on each scale, you get an average improvement of epsilon n to the 1/3. And so then by adding up over enough different scales, you can get an improvement that's a big constant times n to the 1/3. And overall, that's enough to show that the mean is bigger than 4n. And then superadditivity finishes things up. Okay. And so just one other trick that we had was, okay, it's not that easy to say sort of like, what is the distribution of excursions away from the diagonal that the optimal path has? How many excursions do you have of length of order k? So instead, we looked at a sort of different model where we took the diagonal and sort of randomly translated it by a factor by a distance of order, like something between 0 and n to the 2/3, and showed that it was enough to show sort of that in the translated model that you got a large enough increase. And essentially that had the effect of saying that rather than looking at excursions with respect to the diagonal, we could look at a random point on the path and look at the local behavior of the optimal path around a randomly chosen point. Okay. Okay, so I said that the idea was to pick up improvements on sort of a geometrically growing range of scales. So in order for this to work, we'll need, if epsilon is small, we'll need a lot of scales, which means that n will have to be very big. And so the following result is sort of to explain why sort of just doing simulations would make it challenging to decide whether or not epsilon c was equal to 0 or not. And what we show is that if you look at this sort of, the law of large numbers, rate minus 4, it obviously decays to 0, and it decays to 0 faster than any polynomial. So actually, it's not the right thing to expect a power law sort of behavior around the critical value. It's faster than that. And actually, the one prediction for this is that actually it should be something like e to the minus a constant over epsilon. You imagine if epsilon is small, this becomes very small. Yeah. So I mean, I didn't say that this was a. I think this one was. I thought it was from Leibowitz's paper. Yeah. So and we're not going to be able to prove anything like this. Yeah, but sort of faster than. But to say that it's faster than polymer. Okay. So understanding the way in which okay, so yeah, there's a couple of lines here that aren't showing up very well, but you should imagine that the picture looks like this, the rectangle divided into 3 thirds. Okay. So imagine we take a rectangle of length, and so it's going to be sort of parallel to the diagonal. The length on one side will be n, and on the other side will be n to the 2/3. That's sort of the right thing to look at with respect to the transversal fluctuations. And now for every point on the left and every point on the right, we draw in the shortest path from the left to the right, or the optimal path, and just draw in all the n to the 2/3 squared set of paths. So on the left-hand side, it's going to be a mess. There's going to be lots and lots of paths because but as you get more to the middle, they'll sort of coalesce into sort of the best sort of highway to get from one side to the other. And then at the other end, they'll sort of, again, split up into lots of different paths. So on the middle third, which was sort of hidden here, but so let me. So the picture is supposed to look something like this. So on the two sides, the picture is very complicated, but in the middle, you'll see only a small number of distinct paths. And in particular, the result is that the expected number of paths you see here will be a constant independent of n. And actually, it will have sort of quite good tails on the number of paths that you see there. Okay, and And the reason for this is essentially, okay, so the geodesic, these optimal paths, the geodesics they can't intersect in complicated ways. You can't have one optimal path that looks like this and another one that looks like this, because these can't both be optimal paths, because there's sort of a shorter way around this loop here. And because the exponential random variables are continuous, you don't have any ties as well. Okay, so these optimal paths, they can cross, they can coalesce with each other, but they can't form loops. And so if you have lots of paths in the middle third here, what you could show is that there's somewhere, there'll be some, if there were too many paths there, you could find sort of some window in which you have sort of lots of disjoint paths crossing here. And you can essentially, and you can show that this can't happen. It's essentially a consequence of the fact that if you restrict a path to a very narrow tube, then in expectation it will be, or the expectation will be much smaller than if you don't restrict it, and then you can use the BK inequality to show that you just can't have too many disjoint paths in a strip like this. Okay. So with that, we can look at the total amount of time that a geodesic, say the optimal geodesic from 0, 0 to NN could spend on the diagonal. Okay, so here we've drawn all of the paths, but there's one that sort of starts at the 0, 0 and ends at NN. And let's look at how much it intersects the diagonal, the red line, in the middle third. Well, in the middle third, it has to be one of these small number of geodesics. So how much time can they spend on the diagonal? Well, so the idea is, suppose we randomly shifted the underlying field of exponential random variables perpendicular to the diagonal, so in the direction of the green arrows. So if you shift everything, if you shift the field, then you would shift the optimal paths between points in that direction as well. But if you translate the field, I mean the distribution is of course invariant according to that, so you're not changing the expected value of the path from the 0, 0 to NN. So actually we could just take this, so shifting all the field is the same as just shifting the diagonal here to another line in this, like a parallel line in this box. And the expected intersection will be the same. So we could just say, if I take a random line parallel to the diagonal, what's its intersection with all of these curves in the middle third? Well, there's only a constant number of them. Their total length will be a constant times n. The number of translates is n to the 2/3, so the average intersection will be like a constant times n to the 1/3. So from knowing that you only get a small number of optimal paths in the middle third, that will say that the intersection of the optimal path and the diagonal in the middle third has expectation of order n to the 1/3. which was the heuristic we had before. So, yes. Yeah, so I take, every optimal path from the left to the right. And by the time you get to around the middle, like I'm saying the middle third, but it could be the middle 95%, then you're only going to see a constant number. Okay. So this will say that for the middle third of the diagonal segment, the expected intersection will be only n to the 1/3, and then you can sort of iterate this argument on like the segment from 1/6 to 1/3 and sort of sum those up, and you still get a bound of n to the 1/3. Okay. Now, for our purposes, it will also be important to have a sort of concentration, and you can also get concentration on this scale as well. So the time spent on the diagonal divided by n to the 1/3 will have sort of some nice exponential tails. One way you can see this is by... I'm going to now split things up into multiple boxes, and on each of these boxes, look at the middle third. So how much time the optimal path spends in each of those windows, and by using by translating these windows independently of each other, you can get that essentially or stochastically dominate the amount of intersection with the optimal path by a sum of independent random variables. Okay, but now if you just think about doing that argument naively, you'll lose a lot because you're not really using the fact that some of the time actually the optimal path should be a long way away from the diagonal. But we already know what the mean is on all the different scales, and so if you do that, and you can get the right that sort of saves the inductive analysis. So you can get concentration on the right scale. Okay. So ultimately our analysis is going to be sort of a more complicated version of this, where we look at not just the best paths, but paths that are close to the optimal one too. Okay. So we want we'll do a sort of inductive argument on a series of geometrically growing scales. So epsilon is the rate of reinforcement, and n0 will just be 1 over epsilon, and that will be the smallest length scale we look at. And nj will be like n0 times n0 to the j over 100. So it's growing by sort of a small polynomial factor of epsilon on each for each j. And now we'll look at a rectangle of length nj on this side, and n to the 2/3, nj to the 2/3 here, times an extra logarithmic factor, which will be sort of enough to make sure that all of the transversal fluctuations stay within the range that we're looking at. And so our inductive statement will be to say that if I take any u on the left side and any v on the right side, and look at the optimal path in the reinforced environment minus the passage time in the unreinforced environment, then the difference is at most this term. So the main term here is, so if nj to the 1/3 would be just the normal sort of fluctuations that you expect. Then we have an epsilon to the 1/3 there, which is sort of the, okay. So this is something very small. Remember, epsilon and nj will be sort of like related to each other by polynomial factors, and then a bunch of logarithmic factors. And we're going to do this analysis up to this induction some number of times, k epsilon times, where k epsilon will be a function of epsilon, and it will tend to infinity as epsilon goes to 0. We won't be able to keep doing the sort of inductive analysis arbitrarily many times, because eventually the, you know, because for large enough distances, this difference will become linear in nj rather than a power of 1/3. Okay, so this is the inductive sort of statement that we want to prove. And the point is that this value here is much smaller than nj to the, well, will be much smaller than nj to the 1/3, so much smaller than the order of fluctuations you expect to see in a rectangle like this. Okay. So now we want to do the induction and go to the next scale, j+1. So we have a rectangle of side length nj+1 here and nj+1 to the 2/3 here. And we want to sort of work out how much, you know, what's the biggest value of this improvement for any starting point on the left here and ending point on the right here. Okay, and so, you know, you only get an improvement when you're actually on the diagonal. That's the only thing that's changed. So we want to bound the total number of times the path can hit the diagonal. Okay. But of course, I mean, but what paths are you allowed to have? Well, they have to be, so they can't be paths that are much worse than the original one. And so in particular, the biggest improvement that you could hope for is just the sum of the improvements on each of these segments here. And so, sorry, I'll split the diagonal up into segments of length nj. And so if it hit all of them, so the number of segments is nj+1 over nj. The improvement in each segment is at most this. So the total improvement you could ever get would be, say, nj+1 over nj times this term, which will be epsilon to the 3rd, nj to the 3rd. But this ratio is equal to epsilon to the 1 over 100. So we'll still get something that's, okay, so all up we'd get epsilon 1 over 100 plus 1 over 3 nj to the, okay. And this is less than or equal to, say, epsilon to the 1 over 10. Yeah. Oh, sorry, this is minus. So. Okay, so any path that we could possibly consider has to be within at least epsilon to the 1 over 10 times nj+1 to the n3rd of the optimal path. Otherwise, there's just can't get enough improvement from the diagonal for it to be competitive with the original optimal path. So I'll call a path sort of almost optimal if it's within this of the optimal path for that particular pair of endpoints. Okay, and to do the induction, we're going to show that for any almost optimal path, the number of segments on the diagonal that it hits is essentially the total number of segments to the 1/3 times some extra logarithmic factor that we'll lose. Which probably shouldn't be there, but for our purposes, it won't really matter. Okay, so that's the final thing that we need to show. And the way we'll do it is by saying that if we essentially take any line here, sort of parallel, so in the middle, parallel to the short end of the rectangle, split it into segments of length, essentially nj to the 2/3, the number of these segments that are hit by almost optimal or almost optimal paths will be something close to a constant. Maybe not a constant, maybe we'll allow it to be logarithmic. So even the almost optimal paths will have coalesced enough so that they don't hit many of these segments along there. So that's the statement we want. So this is very similar to the statement we had before for optimal paths, but now we have to allow the sort of almost optimal ones as well. And if we have this statement, then essentially by doing the sort of translation arguments and concentration, we'll be able to establish that any almost optimal path doesn't hit too many segments, doesn't hit the diagonal in too many of the segments down here, and that will allow us to finish the induction. So what's left is we want to show that the optimal or almost optimal paths don't hit too many of these segments. So the idea will be as follows. Just take two vertices, like one on the left and one on the right. Then there's some optimal path between them. But there may, and now there may be some almost optimal paths as well. Something like this. Okay. For a typical U and V, actually the way we've chosen the parameters, you don't expect there to be any other segments hit by almost optimal paths. Because essentially the definition of being almost optimal has this sort of power of epsilon in front, but small enough that essentially it means that the cost from going through this point and this point have to be almost a tie, and that will just be very unlikely. And now, the trickiest part is to show actually you're unlikely to have more than, it's very unlikely to have more than a constant number of segments hit for any fixed U and V. And for this, requires some sort of quite detailed calculations, but essentially that you can, but it's actually not asking a very strong statement, because even saying, well, what's the best path that goes through here and the best path that goes through there, are they within sort of this range of tolerance? they're going to be very unlikely. That's going to be very unlikely, and so unlikely that even it's unlikely you find any pair which are equal. And so then you want to say, okay, that with high probability you only get a constant number of these intersections. Although to make it even easier, it would be enough for us to just have a logarithmic number of segments. Okay, so we do this for one set of points, and then we do it for every pair of points here. So this one maybe has another path here, and maybe it also has another, say, almost optimal path that does something like this. Okay. So how do we analyze this? Well, okay, for each U and V, all the segments that they have almost optimal paths going through, we're going to give a rank to. So the optimal one will get a 1, then the second best one will get a 2, and the third best one will get a 3, and so on. And we'll do this for every pair of U and V. So this one gets a 1, and then a 2 here. And so for each segment, we'll get a series of ranks. And sort of the overall rank of a segment will be the minimum value it gets from any pair of points on the left and the right. So the overall ranks would be 1 here, 2 here, 3 here. This one had a 1 from one path and a 2 from another, so it gets the minimum one, which would be a 1. Okay. And now we bound separately the number of the 1 paths, the 2 paths, and the 1 segments, the 2 segments, and the 3 segments, and so on. Okay, and why do we want to do something like this? Well, suppose we had 2 segments, both of which get a k. Now, since they have a k, it means that there's a kth best almost optimal path through this one, and a kth best almost optimal path through this one. And the claim is that you can't have this picture. The reason is, okay, we formed a loop like this. So there's 2 ways to get from here to here, and one of them is better than the other. Let's suppose that the top one is better than the bottom one. So it means that this green path is better than this yellow path. But this yellow path was the kth best sort of segment for an almost optimal path. So this green one will also be an almost optimal path, but will pass through this segment up here, and so this must be like a k-1 almost optimal path. And so, but so therefore we shouldn't have labeled it as k. Okay, so what that says is that the almost optimal paths of rank k, we can take them so that they don't intersect on both sides of this line. And so if they don't, and then if they don't intersect on both sides of the line, then we can take, we'll be able to find a segment where we have lots of ones that are all disjoint from each other, and we can apply the same sort of argument that we had from the earlier works that you can't have many disjoint paths, all of which are good. And from that you can sort of complete the induction and sort of establish this result, then go back and establish that you don't hit more than sort of 1/3 power of the number of segments along here. Okay, well, thanks.